Diesel cycle. How does a diesel engine differ from a spark ignition engine? What cycle does a diesel engine work on? A diesel engine works on a four-stroke cycle. The first stroke is the intake stroke. The piston moves down and it draws air into the cylinder. Note that this is only air. There's no fuel mixed with it. The second stroke is the compression stroke. The piston moves up and it raises the temperature and pressure of the air in the cylinder. Just before the piston reaches the top dead center, a fuel injector injects a spray of fuel droplets into the cylinder. Because the temperature and pressure are high, these droplets evaporate. The fuel vapor ignites spontaneously, and the combustion increases the temperature and pressure in the cylinder even more. This leads to the power stroke. The piston moves down. And then finally, the exhaust stroke. The exhaust valve is open, the piston moves up, and it pushes the exhaust gases out of the cylinder. These four strokes are repeated to form the diesel cycle. We can draw the indicator diagram for the diesel engine, which records the pressure inside the cylinder as a function of the gas volume. We mark on this the atmospheric pressure. We also mark the minimum volume, which is when the piston is at TDC, and the maximum volume, when the piston is at BDC. During the intake stroke, the volume increases from Vmin to Vmax, and the pressure is just slightly below atmospheric. Once the piston reaches BDC, we have the compression stroke, and the pressure rises inside the cylinder. Just before we reach TDC, we have the ignition of the fuel. Now the fuel is evaporating and it is burning. This is not like a spark ignition engine where the ignition and combustion is almost instantaneous. The combustion of a liquid fuel is a much slower process because the liquid first has to evaporate and then react. So the pressure remains roughly constant until the combustion ends. Once the combustion ends, then the pressure starts decreasing inside the cylinder as the volume expands. Just before the piston reaches BDC, the exhaust valve opens and we get a sudden drop in the pressure inside. Then, during the exhaust stroke, the pressure inside the cylinder remains just slightly above atmospheric. We can draw an idealized PV diagram based on the indicator diagram. There is no work done in the exhaust in the intake stroke, so we can neglect those. The compression can be idealized as an isentropic compression. The heat addition process, which is when the fuel is burning, can be approximated as a constant pressure heat addition. After that, the expansion process is an isentropic expansion. Once the exhaust valve opens, the drop in pressure is very rapid, and we can approximate that as a constant volume heat rejection. A diesel cycle can therefore be represented on both PV and TS diagrams. We have first the isentropic compression, which is a vertical line on the TS diagram, the constant pressure heat addition, the isentropic expansion, and finally the constant volume heat rejection. We can define what is known as the cutoff ratio, R sub C, which is defined as being equal to V3 divided by V2. V3 is the volume at the end of the heat addition step. V2 is the minimum volume when the piston is at TDC. V3 is determined by the duration of the fuel injection. The faster the fuel injection and the faster the combustion of the fuel, the smaller the value of V3. Process 2 to 3 is at constant pressure, so P3 is equal to P2. We can write the ideal gas equation between points 2 and 3. So T3 upon T2 is equal to P3 upon P2 times V3 upon V2. P3 is equal to P2, so they cancel out. So T3 upon T2 is equal to V3 upon V2. So the cutoff ratio is given either by V3 upon V2 or by T3 upon T2. We can then do an energy balance to determine the heat transfer. The heat added, QH, is equal to H3 minus H2. This is a constant pressure process. So this is equal to Cp, T3 minus T2. The heat rejection is a constant volume process. Therefore, Qc is equal to U4 minus U1, which is Cv, T4 minus T1. We can now determine what the thermal efficiency of the diesel cycle is. The thermal efficiency is defined as the net work output divided by the heat input. The work output, Wnet, equals QH minus QC. So the efficiency is equal to 1 minus QC divided by QH. We can now substitute the values that we have for QC, which is Cv times T4 minus T1, and for QH, which is Cp, T3 minus T2. Cv upon Cp equals 1 upon gamma, where gamma is our specific heat ratio, Cp by Cv. We can write the thermal efficiency then as being 1 minus the numerator we write as T1 times T4 divided by T1 minus 1. The denominator now becomes gamma times T2 into T3 by T2 minus 1. T3 upon T2, we have just shown, equals the cutoff ratio, or C. We now need to determine what the other temperature ratios are. The process 1 to 2 is isentropic. So we can write T1 upon T2 as being equal to V2 upon V1 to the power gamma minus 1. The compression ratio R, which is Vmax upon Vmin, which equals V1 divided by V2. We can therefore write T1 upon T2 as being equal to 1 upon R to the power gamma minus 1. Process 4 to 1 is at constant volume. We can therefore write the ideal gas equation between point 1 and 4. V1 is equal to V4 because 1 to 4 is a constant volume process, so the volumes cancel out. And T4 upon T1 is therefore just equal to P4 upon P1. Now let us divide both the numerator and the denominator by P3. Process 2 to 3 is at constant pressure. So we can write T4 upon T1 as being equal to P4 upon P3 divided by P1 divided by P2. And we replace P3 by P2 because they're equal. Process 1 to 2 and 3 to 4 are isentropic. So we can replace both the pressure ratios by the volume ratios. So P4 upon P3 equals V3 upon V4 to the power gamma, and P1 upon P2 equals V2 upon V1 to the power gamma. Now V1 is equal to V4, so those two cancel out. And T4 upon T1 therefore equals V3 upon V2 to the power gamma. This is equal to the cutoff ratio, RC, to the power gamma. Now we can go back to the expression that we had derived for the thermal efficiency of the diesel engine. And we can start replacing the temperature ratios by the volume ratios that we have just derived. T3 upon T2 is the cutoff ratio, RC. T4 upon T1 is the cutoff ratio, RC to the power gamma. And T1 upon T2 is 1 upon R to the power gamma minus 1, where R is the compression ratio. So our final expression for the thermal efficiency of a diesel engine is in terms of gamma, the specific heat ratio, R, the compression ratio, and RC, which is the cutoff ratio. Now we can compare the efficiency of the diesel and the Otto cycle. This is the expression that we just derived for the efficiency of a diesel cycle. This is the expression we had previously derived for the efficiency of an Otto cycle. We can see that the difference is that term in brackets. This term is always greater than 1. Therefore, for the same compression ratio, the thermal efficiency of a diesel engine is less than that of an Otto cycle. Also, we can see that reducing RC increases the efficiency of a diesel cycle. The faster we can inject the fuel, the more efficient the cycle. Of course, this is limited by the pressures at which we can inject and the rate at which the fuel will burn. Now, diesel engines have only air in the cycle during compression, which means knocking is not a problem for them. We do not have auto ignition of the air-fuel mixture. So therefore, they are not limited in the same way that the spark ignition engines were. Diesel engines can have higher compression ratios, and typical compression ratios can go from 14 all the way up to 23. To summarize, in diesel engines, liquid fuel is injected into the cylinder. There is no spark plug, and the fuel is ignited due to compression. There is no knocking in the engine since fuel is injected at the end of compression. Diesel engines have higher compression ratios than spark ignition engines and therefore have higher efficiencies.